आजको हाम्रो मुख्य प्रस्तोता हुनुहुन्छ प्रोफेसर डाक्टर होमनाथ ढकाल सर, जस आजको मुख्य टपिक रहेको छ टुवार्ड्स एचिभिङ सर्कुलर इकोनोमी एन्ड कार्बन नेट जिरो थ्रु द सस्टेनेबल मेटेरियल्स, जो हाम्रो डाक्टर होमनाथ ढकाल सर चाहिँ प्रोफेसर मेकानिकल इन्जिनियर एट द युनिभर्सिटी अफ पोर्ट्समाउथ इन इन्क्वेमा लामो अवधि कार्यरत हुनुहुन्छ। उहाँ नेपाल आएको अवसरमा सोनेकीको कन्डिसनमा आजको हाम्रो यो कार्यक्रम सञ्चालन गर्दैछौँ।
Very important for achieving research aspiration, research outputs, I would say. So in that sense, I'm very happy today to be here. So as the topic is clear, that towards achieving circular economy and carbon net zero through sustainable materials. So that is the topic. So let's hope I will be able to communicate some of the things that we have been doing towards this direction in UK. And also I'll try to bring some context together. I would like to say something before I start, because this event holds special significance to me personally, because I graduated my engineering certificate in engineering from Faculty campus. Then I joined Institute of Engineering Pulcho campus as a research assistant in 1988. That's how I started my academic career. So this is coming home for me. So that puts very special significance to this event. And I'm sure those participating online can be my respected professors, my teachers, my fellow colleagues, and my students. So from that point of view, again, it is very important for me, and I'm very happy to be here. The quick outline, I would like to talk about sustainable development goals and circular economy. Then I will be talking about sustainability and sustainable development. We cannot bring net zero and circular economy without talking sustainability and sustainable development. Then we'll be talking about circular economy versus linear economy. We'll be comparing them. And then I will be talking about value creation through sustainable materials. And then I would like to bring some sustainable materials, potential for lightweight applications or further advanced applications. And then I would like to also discuss some results that we have obtained through various research. And then I would like to just bring conclusion and future perspectives. So as I'm from University of Portsmouth, as our Dr. Dithal introduced to me, I'm from University of Portsmouth, UK. Portsmouth is a very beautiful city located next to the English Channel, southwest of England, and it is also called home of Navy. We have big naval center, and University of Portsmouth is very importantly placed in Portsmouth. So we have got amazing achievement. We are TEF Gold University, we call it. In UK, we have every 4 years teaching excellence framework and the research excellence frameworks that happens. The government measures academic institutions' performance in terms of teaching as well as in terms of research. There are different criteria for that. So number of publication, number of PhD completion, number of income you generated, number of research output. There are so many criteria they measure against. So that is called REF, and the number of criteria they measure again on teaching. So we are teaching excellent TEF University, TEF Gold University. So I'm very proud to say that. So also we have about 23,000 students, 2,500 academic staff, and School of Mechanical and Design Engineering, where I work, is one of the largest schools in the university. And university has significant investment, and one of the investment I can bring that is we call Future Technology Center. It is a 12 million investment, where university invested 6 million, and we got funding from government another 6 million. We have many facilities that I would like to quickly highlight that to you, and then I will go to the main topic. Obviously, Advanced Polymers and Composite Research Group, which research group I lead. We have various members, multidisciplinary team. So this research group is within the School of Mechanical and Design Engineering. So we have multidisciplinary team of researchers focusing on design, development, testing, and characterization of sustainable polymers and composite. We have 3 other research groups within the School of Mechanical and Design Engineering. So I just would like to highlight some of the work that we have been doing within the research group. Mechanical testing and characterization is one of the key areas that we focus when we develop new materials. Obviously, you want to test how this material perform, how resilient that material is. Of course, that depends on your application areas. If you are using that material for space application, then you'll be looking about strength, stiffness, lightweight, cryogenic condition, that how material behaves under UV exposure, under minus 300 degrees centigrade, how that material performs in terms of mechanical performance, thermal performance. So testing and characterization is very important when you develop new material. So that's what we do. So within that we have modeling, we have got machining of these materials, because we also use this material for different application. This application include aerospace applications, automotive application, marine applications, renewable energy application, building and construction application, packaging applications. So when you are working in different areas, you develop different materials. And different materials, you got different performance target. So that is what we do here. So we do modeling of work. Within the mechanical testing, tensile, three-point bending are very classical testing. We do fatigue testing, we do creep testing, we do low velocity impact testing on these materials. If you are using this material for automotive application, for example, for front bumper, rear bumper, or parcel shelves, door linings, whatever. So then we also have got amazing facility on 3D printing, because advanced manufacturing is very important at the moment, and advanced manufacturing leading to advanced material cannot be isolated from advanced manufacturing. So 3D printing is one of our manufacturing technique we use, and then we obviously need to characterize. For that, we need to have X-ray microsity, how you develop 3D printed parts, especially aerospace application areas. You need to be very focused. So we try to work on this 10-point plan for green industrial revolution that UK government has set. So our aim is working towards those goals, especially focusing on advanced materials and renewable energy sector. So University of Portsmouth have two thematic areas that directly contributes towards 10-point plan for green industrial revolution of UK government. So that is sustainability and the environment, future and emerging technologies. So these two research thematic areas of research is directly related to our research. Okay, so I would like to just show some of the facilities that we have. So I was referring earlier, Future Technology Center on the right-hand side, amazing building. We have got amazing facilities in that building. Within that building, we have got three amazing conference space. We have conducted so many conferences there in a very friendly environment. Then we have got 3D printing for polymeric material and 3D printing for metallic materials. So these are some of the parts that we produce using our machines. So key industry application that I can say is automotive sector, defense sector. We are working aerospace sector, and obviously marine sector, and then renewable energy sector, and then also biomedical sector. So these are the key sectors that we have been working within our 4 research group that I mentioned earlier. So going back to the topic, sustainability and sustainable development. Well, when you talk about sustainable development, what it comes to us, we always remember that particular definition. Meets the need of the present generation without compromising the ability of future generations to meet their needs. So the way you are using materials today does not follow that definition. So we are using materials far, far more than we can cope. So that is not sustainable development. So if we want to achieve sustainable development, we have to leave something for our future generation. So that is the definition I always like when I talk about sustainable development. Obviously, when you talk about sustainability, then you are talking about it has to be means. You have to have enough means to achieve what you are trying to achieve. So you have change in a balanced fashion in which the exploitation of resources, direction of investments, and technological development, as well as changes in the society, are in harmony and enhance current and future potential to meet human needs. Aspirations 2030 agenda by United Nations. That's quite interesting sustainability definition. So these two things come together, sustainability and sustainable development. So let's look at the context here. So the way we are using materials at this time is not sustainable. So the plastic being used 90%, as of 2015, so I just got this data from Alana MacArthur Foundation. So here we can see 2015, approximately 6.3 billion tons of plastic waste had been generated. Plastic waste been generated. 9% recycled, 12% incinerated, 79% accumulated in landfills. So that is significant amount of materials that are being thrown to landfill. So that is one thing just to keep in mind. So if you go to plastic bottles, for example, single-use plastic bottles, is a huge amount of plastic bottles are being thrown into landfill again. And if we go to different materials and how long it takes for them to degrade, you can see on the right-hand side, some material it takes 50 years to fully degrade or biodegrade. Some materials takes even 200 years, some plastics. Some plastics takes about 450 years. So these are very harmful materials, plastics, that we have been throwing to the landfill. So just remember that in context. So the use of plastic is just increasing exponentially. So that is what we can see on the left-hand side. And if we look to the right-hand side, just talking about plastic packaging materials. So there are, again, a lot of materials being thrown into the landfill. Very small amount of material have been recycled or incinerated. So this is the context. So, well, 17 goals. So whenever we prepare our publication paper, we always think about ourselves, which of the sustainable 17 goals this paper attempts to achieve. So it's always a good idea to look the sustainable development goals, 17 goals, and just look your publication or the paper you are trying to submit to publish, and which goal or which are the goals that you are trying to achieve. So here I just like to talk a few topics, and then it will be very clear the circularity and net zero importance. So on the left-hand side, obviously me coming from a composite materials background, so I would like to bring composite material application example. So we are also member of Composite UK, which is trade association, which has got many, many members, and there is a sustainability subgroup, which I am member of sustainability subgroup. I mean University of Portsmouth and our research group. So if we look here, 98% of reinforcement for fiber composite materials, which comes from glass fiber, is non-renewable. It's very difficult to recycle. 98%. So that is a big number. So it is driven by cost and functionality and performance. Because if you talk about composite materials, there are matrix materials which comes from thermosets and thermoplastic, and the reinforcement material comes from natural materials and conventional synthetic materials. We also call them non-renewable reinforcement, which include carbon fiber, glass fiber, aramid fiber. These are basically man-made fibers. If we look life cycle assessment of these materials, for example, and then compare that to natural plant fiber composite materials, which I'll come a little bit later, their environmental performance is far poor. That means their energy consumption is very high. Compared to carbon fiber, natural fiber is nothing almost. Glass fiber has got still high carbon emission. When you talk about life cycle assessment, obviously, I don't know how many you are aware of life cycle assessment. If you want to measure the environmental performance of a material, you conduct life cycle assessment. So you talk raw material extraction, how much energy it consumes, raw material production and processing, how much energy it consumes, and use of that particular component, and then how many years is the life of that particular component or part, and how you are going to tackle end of life, how you are managing it. Are you recycling it or are you throwing to the landfill? So you measure each stage, material extraction, production, use, dispose, transportation, and then you calculate overall environmental performance. So this material have high environmental consequences compared to natural material that I will come later. So that is one scenario. Can you see here? The glass fibers are being used in the composite sector. 98% of them are coming from non-renewable sources. If you go in the middle, in 2018, the plastic used and plastic generated by the industries, can you see packaging only comprising 46%. So packaging material comprising 46% of non-renewable polymers. That is another striking information here. So if you go to aerospace industry, for example, 50% of the material they use, for example, Boeing and Airbus, they use 50% of their material is carbon fiber. So if one Boeing makes 50 aeroplanes and Airbus makes 50 aeroplanes, and let's consider the life of the airplane is 20 years. After 20 years, you have massive amount of carbon fiber coming from waste material. So how you are going to manage that? The life cycle, when you compare life cycle assessment, carbon fiber has massive amount of energy consumption compared to glass fiber and natural fibers, for example. Natural plant fibers. So just to think about that. So automotive industry, again, if you go to marine industry, so the use of sustainable materials has become challenge. Now consumer pressure, government legislation will not allow that you used to do 10 years ago or 15 years ago. Okay? So the scenario here is on the right hand side, the way we are using materials, it's just the population growth and materials use is just massive. It's just there is no sustainability. You cannot cope it. If you are going to use in that current rate with the current technology available, then we are needing not only one Earth, we are needing 3.5 more Earths. So we are not getting 3 and more half Earths. We have only one Earth available. So this is the significant. This is the context that we are talking about: circularity or circular economy and net zero. Well, I found this very interesting paper. It talks about growth, but it was warned by different authors that 50 years ago the book was written, and which argued that exponential growth could not go on forever without catastrophic damage to the environment. So the economic growth is great. We need that. But what is the balance between economic growth, sustainability, and environmental aspect? So those balance has to be made. So you can see 50 years ago, the different people had warned our development is amazing, it's exponential growth, but it will bring catastrophic outcome. And that is what it is. So the growth was only focused on material, performance, and economy. But here, this article talks about green growth, higher living standards, healthier environment is important. So to do that, you have to go back. So for that, there are many different countries placing net zero or zero carbon by 2050. So we can see different countries. If we talk about UK, obviously what you produce now and what you, your material consumption and what you are contributing to the environment has to be balanced. So that is what UK government has put a net zero target. Similarly, so many governments in the world has put a net zero target, and accordingly they have net zero strategy. Right, so circular economy, I don't know how many of you are aware of circular economy. Circular economy seeks to rebuild capital, whether this is financial, manufacturing, human, social, or natural. So it ensures enhanced flows of goods and services. The system diagram illustrates the continuous flow of technical and biological material through the value circle. So you are using material again and again and again as much as possible. So you may have one product that has 10 years of life. So if you want to reuse that material, you have to think about that material, how to reuse, how to manage end of life cycle in the design stage. So that you know after 10 years or after 20 years, or even after 5 years, if you talk about, let's say, turbine blade made of glass fiber, epoxy or polyester matrix, that has 20 years of life. So after 20 years of life, what are you going to do? You have to think that in design stage. And after that, you need to reuse that material. It may not be for turbine blade, used for another application where that material can be reinforced as a new material. So this is cycle 1. And then after that, that material has got also life cycle, maybe 10 years, because if you are reusing that particular material, instead of 20 years of life cycle, it can go 15 years of life cycle. Okay, performance reduces when you recycle it. Then after 10 years, 15 years, then reuse it again. So again and again, we call that cascading. Okay, so the circular economy, this is quite a nice diagram. I like this diagram. I don't know whether you can read it. I also can hardly read it. Wow. Okay, so obviously, you think about reducing the material use in the design stage. Okay, and then you redesign. You think about design. So okay, how can you use this material? Again, you think in design stage. We call design for manufacturing, design for assembly, design for reassembly, design for recycling. So that is the concept you use in design stage. I don't know how many of you are familiar in these approaches. Design for recycling. So at design stage, I teach this subject to my students. So at the design stage, you need to think about how you are going to manage the end of life option of this material or product. And based on that, you choose particular material, particular manufacturing process. So design for recycling. Design for assembly, how easily you can assemble that material. Design for disassembly, how easily dismantle that material so that you can use that in another application. Okay? And design for environment. So environmental aspect has to be thought in the design stage. So that is what it is here. And then if you go to number 3, reuse. Number 4, repair and remanufacture. Number 5, recycle. Number 6, recover. Number 7, dispose. You only dispose at the end of all the cycles. You have exhaustingly used them, and then finally, only very small percent of material you can dispose. So that is the circular economy. And people think that, well, this is very demanding approach. Business think that we may not be able to, implement this kind of approach. We might lose our profitability, or it might be just difficult to continue, but that is not the case. This approach will bring a lot of benefit, a lot of success in the long run. So this is circular economy. I think it will be quite easy to understand linear economy. We also, okay, so here circular economy is not just recycling, it's far, far more than recycling. So this is just an example, different sustainable development goals, how they are achieved, and we can see different United Nations environmental related convention here. 2009 Copenhagen, you wanted to increase the temperature limit the temperature up to 2 degrees. Then we had 2011, and then we have got Paris Agreement 2015. You have to keep the pre-industrial level temperature 1.5 degrees centigrade. If you go more than that, there are consequences. And then 2021. COP26, which is held in UK, Glasgow. I had the opportunity to talk a little bit about our preparation for COP26 within our research group. So these are the some of the events that has taken place. So my focus here is circularity or circular economy is not just recycling, it's far more than recycling. So going to linear economy, I think linear economy we call take, make, waste, and repeat. Take, make, waste, and repeat. That is the linear approach. So that means you don't think about what happens in the future, how you are going to manage end of life option of the material. You just extract the materials, you make what you want to make, use manufacturing technique, what is suitable, convenient to you, and use the material. After end of life, you throw the material. So that is linear economy. So what are the consequences of linear economy? Well, you extract material, you use energy. You manufacture materials, you use energy. You distribute material, you use energy. You consume materials, you also use energy. Okay? You dispose materials, you use energy. So you are all the time using energy, and you are not thinking about consequence of those energy uses, for example. So that is linear economy. So what happens with that? Air pollution, solid waste, resource depletion, biodiversity loss, extreme weathers, that is what we have been experiencing in the last 5 or 10 years. All of a sudden, the weather in the UK, 2 years ago, we had such a warmest summer. Warmest summer, yeah. We never had that kind of experience because UK is not prepared for that. Because UK has got no, no air condition. We only have got a radiator that is for winter. We have nothing for summer because we never had used to that kind of temperature. People died because of heat wave. Many elderly people died. So we are not prepared for that kind of weather, but we had that kind of weather. So can you see the extreme weather coming without noticing? We can see bushfire in Australia. We can see hurricanes in the USA. We can see so many disasters. So that is what happens when we follow linear economy. And then obviously the harmful effects to human health and planet health, obviously. So you can see that this diagram, I like, this is a very serious diagram. Polar bears may be gone forever if we continue follow this linear economy principle. Yeah. So with that, I just wanted to give one example here. This work was particularly done within a project called CBICOM within our research group, University of Portsmouth. We had 11 different partners. This is an Interreg European project. I was principal investigator for University of Portsmouth. So here, what we did was just talking about linear economy. What is happening is that you are damaging human health and planet. So this is one of the examples is the debris, the plastic particles being thrown to the sea environment. So we did look conventional polypropylene and then PLA, polylactic acid, which is biodegradable polymer, which can be recycled. And polypropylene is the industrial polymer, which is very difficult to recycle. Yeah. So we did a microplastic formation of these two materials, and then we found that PLA was far better for microplastic particles release compared to polypropylene. Okay. So if you use PLA for marine application, you have got less microplastics release. So there will be less harmful particles for marine life, for example. So this is just the example of linear economy and circular economy and what are the differences. Right. I have got some example here again, looking different application areas because this is a materials related talk. So I want to bring different materials, different sector, and then how that sector affects or how that sector is doing in terms of the materials management, for example. So here we can go to different areas, aerospace, you can go to marine, automotive, renewable energy, building and construction, defense, textile. So there are so many application areas we can go. I can talk about aerospace related materials, composite materials, carbon fiber, glass fiber, for example. In marine related, I just mentioned earlier, using two different types of polymers, now thermoplastic polymer, conventional polymer, polypropylene, and then I talk about PLA, biodegradable polymer. So here, if we look the polymer use in textile industry, for example, can you see as you move from 1970 to 2015, the rate of using different polymers is just exponential. So that is one example here. If you look on the right-hand side, I also mentioned briefly earlier, the packaging sector, and there you can see textile, 14.5% polymers being used in textile sector, for example. If you go to clothing, they are the second highest polluting material, in terms of water pollution. So if you go to concrete material, building and construction, concrete materials are another material. They consume high energy making of it. So what are things we can do is the composite materials or automotive industries are trying to use lightweight materials. They are trying to use natural materials so that the overall environmental damage can be reduced. So here, I would like to again just go the textile sector. It's just significant amount of materials being thrown into the waste and pollution and landfill So this is a challenge. So if I move further, I don't want to dwell so much on this one. I just want to bring as an example. So 2% recycle from feedstock. Then you have got 12% cascaded recycling. There are 2% losses during the collection and processing. So 73% landfill or incinerated. When there is an incineration taking place, I don't know what happens there. I don't know how much you trust on incineration. You take material, you burn material, you try to recover the energy. While you're burning, how much damage you bring to the environment, I have no idea. But at least there is either incinerated or landfill. But at least there is being some incineration taking place. So if we want to reach 1.5 degree pathway as assigned by Paris Agreement, then our consumption rate has to drop significantly. Our consumption rate, material consumption rate has to drop significantly. If we have current practice, what we are doing, we will be 2.5 to 2.9 degrees centigrade in coming years. So that is, can we afford 2.5 degree to 2.9 degrees centigrade temperature rise? That will be catastrophic. So to bring that, when the places, we talk about net zero places from different countries by 2050, and if we follow that, we will go to 1.9 to 2.1. Optimistic target 1.8. So 1.5 pathways, you have to use you have to significantly reduce the materials use. Right. So the challenges is there. You have got a waste coming, but we don't know how to separate them, how to manage them, how to recycle them. Well, we don't know. Or maybe we know, but we don't have maybe enough technology available. Maybe we don't have enough research conducted. So I cannot say we don't know. Obviously, we are doing something towards that, but maybe not in effective way. Okay, so this is just an example. I don't know, maybe you are familiar with some of those places. So here I just have brought another example, challenge as a consequence of waste management in developing countries. So it's just the marine waste. When you throw the marine waste, what happens? So many bad things happens. Okay, I don't need to go all. So you have got environmental problem, obviously. You have social problem. You have got economic problem, because if you throw everything around, then tourists will not like it. They have different expectations when they come to certain place. And when they see these kind of things, and then they get upset. Obviously, then public safety also matters. When you walk there, and when you go around, when you go for a morning walk, you want to go for running, so that is not really a good idea. So the idea here is that source reduction, use as less material as possible. If you cannot do that, reuse material. If you cannot do that, recycle material. If you still cannot do that, and then you have got resource recovery, incineration. And then finally, very small amount of material can be landfill. There has to be provision. So this is the circular economy aspiration. So if we can do this, then we can help to meet net zero target. So I'm now going to materials and how materials can contribute. We maybe are engineers working on different materials. So maybe it is a good idea to know some of the materials that we are working. Maybe these are sustainable materials. They will help to reduce net zero. They will help to achieve circularity. I think that makes us very happy. Well, so we are working on composite materials, and especially natural plant materials for composite reinforcement. And especially we are using sustainable biodegradable polymers. So here I'd like to bring one of the projects that I was referring to earlier, that is called CBIOCOM project. Whole idea of this project was bio-based thermoplastic composite. Develop bio-based thermoplastic composite. Why thermoplastic? Why not thermoset? Obviously, if you compare thermoplastic composite and thermoset composite has more performance. Thermoplastic composite can be reused, maybe recycled. So there are different, attributes of these two types of materials. But in this particular project, we wanted to develop thermoplastic-based material. Okay, so then we wanted natural materials such as flax fiber, hemp fiber to be used so that we can make this material long-term durable material, and we can use this material for environmental sustainable material, ecotoxicological effects, less effect on marine environment, and then obviously less microplastic formation. And there are different demonstrators that we develop in this within this project. So this was the project that I was involved. So here, what we did was, long-term durability and ecotoxicological effect, and then microplastic formation and life cycle assessment of this material, how they perform. So we looked more biodegradable, more sustainable polymers to use. So for that, we use TPS, thermoplastic straws, and PLA, polylactic acid. These both are thermoplastic biodegradable material. Only problem with these materials are there, obviously, TPS is thermoplastic straws. Mechanically, they are not very strong. The toughness, they have got good property. And PLA is a very good, stiffness was very good polymer, thermoplastic polymer, biodegradable polymer, but toughness, there is not much toughness for PLA. So what we did was we put together this TPS and PLA, we combined them, made a hybrid composite, hybrid material, and then we looked the overall performance. So by doing that, we achieved strength, we also achieved toughness behavior. So it was less brittle. If it was alone, PLA alone, it could have been brittle, but very high stiffness. But then TPS, very low stiffness, but tough material. We combine them together. And then we also use self-reinforced PLA. So PLA is a matrix, and PLA is also reinforcement. So you are talking about fully biodegradable material. At the end of their life, the material can be fully biodegraded in certain conditions. So in terms of natural materials, we use flax fiber and hemp fiber. Flax fiber comes from nature, is a biodegradable material, is a renewable material, and hemp fiber is the same material. Obviously, we have used jute fiber, dead palm fiber, canaf fiber. There are so many other projects that we have used. We have used these materials, but I'm just referring particularly this CBIOCOM project. So, and we look their environmental performance using life cycle assessment. So what is the disposal, contributing towards energy consumption, what is the transportation, what is the use, what is the manufacturing. And in terms of resource depletion, for example, these are the environmental impact categories coming from different processes. Different stages, I would say. Okay, so in terms of resource depletion, how much manufacturing has contributed, how much in terms of use, how much acidification, how much ozone depletion. So again, life cycle assessment is very important to understand and to use. But there are many industries, they still don't use life cycle assessment. They don't have means to use life cycle assessment. So we as an academic institutions, we need to explore this possibility. In this project, we have got industrial partners and academic institutions as partners. So we perform some of the things we perform in university, some of the things we performed in industry. So we bring together our expertise and the collaborative approach, and we try to solve this, understand the environmental aspect of these materials. So then we also looked on seawater aging. If you are trying to use materials in marine environment, what happens if you expose this material under different conditions? If you put in UV, what happens? If you put in seawater, what happens? If you put in hot water, maybe 60 degree, what happens? If you put in 90 degree humidity, what happens? How this material behaves. So you need to understand that. What are the long-term consequences under these conditions and these materials? How much material property is retained, or how this material degrades. So that is very important to understand. So we look this PLA material, and then we put different temperature and different time duration, and then we look their degradation, how they degrade. So low temperature, 12 months immersion, and then how this material behave in terms of weight gain, in terms of stress reduction. Can you see the weight gain and how the stress, how the properties are decreases as we increase the immersion time? So you can see clear influence of aging at 40 degrees centigrade. Under room temperature, not much effect. So it is very important for us to understand this behavior so that we can use this material for marine application. Because these materials are coming from natural sources, PLA, It has got less particles that I referred earlier, microplastic formation, compared to PP and PLA. So PLA has shown very good in microplastic formation attributes. So why not explore this material fully so that we can recommend this material for boat hull, for example. So using materials to reduce environmental burden, using materials, right materials, to reduce carbon footprint. So that was the idea. Then this is very interesting result that we have obtained. This was another project called Flower Project, and this is also a European project. As I said earlier, research cannot be done in isolation. We have to collaborate. So we collaborate different industries and different academic institutions. So in this particular project, it's called Flower Interreg project. It was 4.6 million euro, 4 years long project. So in this project, we did a lot of work. I cannot bring all, but I just want to bring some very snapshot result. We looked PLA, PHA. These are the biodegradable polymers. Then the conventional industrial polymers, PBS and polypropylene. We looked their mechanical performance. And then we put flax fiber and, on PLA and flax fiber on PHA. And then also we put flax on polypropylene and flax on PBS. And we use extruder. Then we look their mechanical performance. You can see here the tensile stress obtained for PHA is 60, PLA is 60, PLA alone. This is polymer alone without reinforcement. And then when you go to the composite material, when you reinforce flax with PLA, then you can see the tensile strength almost 100 megapascal. So that is a significant achievement, because 100 megapascal tensile strength coming from bio-based composite, or this is biocomposite. I don't know how bio-based composite means when you have either polymer or reinforcement, one of them coming from biodegradable source, that's called biocomposite. But this is that's a bio-based composite. But this is biocomposite because both reinforcement and matrix are biodegradable. So biocomposite getting 100 megapascal tensile strength is just amazing. We're so thrilled. So if you go further, Young's modulus, compared to available literature and other materials, and our flax PLA and flax PHA, again, outperform other materials. So we are so proud to get this result through this project. So let me give you an example. If you talk about application, what is the significance of 100 megapascal? Well, if you try to use engine tray in automotive application, OEMs, original equipment manufacturer, have assigned that you need to have at least 100 megapascal of tensile strength for this material. So that is the key target, that if we wanted to use this material for engine tray, 100 megapascal, amazing. After end of life, fully biodegradable. So this is the research that can contribute, can help to achieve circular economic aspiration as well as net zero aspirations, net zero target. So if you wanted to obviously read more about this material, you can go to this journal and you'll be able to read them. And if you don't find, you can email to me. I'll try to send that paper to you. So again, that flax fiber that we researched, and we last summer I was a place called Concarneau that is in France, and one of our partners called Kairos are based in place. Concarneau is a very touristic area, beautiful place in summer, and there we release our boat fully made from flax fiber composite, replacing glass fiber composite with flax fiber composite. And this boat is currently being used. So there was another amazing achievement from this flower project. So there are possibilities if we work together by using sustainable materials and bringing sustainability or bringing circularity or achieving circularity. So this was amazing example, amazing achievement. So I don't want to dwell too much here. So natural fiber reinforced composites are very good for different applications. including automotive application, marine applications, but they have also limitations because if you expose this material under different environment, they swell. And after certain conditions, they damage. Sarojit, you have to warn me if I have reached close to 45. I'm okay. Right, thank you. Because I have not watched my stopwatch. Right, thank you. Okay, so natural fiber reinforced composite. So that is what I was referring earlier. Flax fiber, hemp fiber, jute fibers, canaf fiber, banana fiber. I don't know what kind of fibers we get in Nepal. Obviously, hemp fiber is not approved as a industrial reinforcement, but I think there are so many debates going on at the moment. Flax fiber, alas we call it. I don't know how much we use flax fiber in textile. We can still use that as a composite reinforcement. Obviously, flax fibers are used in textile application, clothing and bags. But if we can use this high-end application, we can move to automotive applications. So obviously, research institutions, academic institutions have to do research. And we have to bring industry on board that we can explore these materials. Jute fiber is another great fiber we have. We are quite rich, not as rich as Bangladesh, but we still have plenty of jute fibers we use for jute baggage and bags. We can also use that material. Maybe the waste jute material coming from that process you can use. Maybe we can use in concrete, for example. So there are so many examples that we can take. We have to do research, obviously. We have to do testing. We have to bring industry on board. What is the application? So we have to do a lot of work. It takes many, many years to bring that products into use, into application. But we can explore. We can always explore. That is research. So natural fiber composites, there are so many advantages we can get from this material. So we have hemp fiber, jute fiber, flax fiber, bamboo is another great example. In Nepal, we have got lots of bamboo fibers available. Banana fiber, canaf fiber, cotton, I think cotton also, sisal fibers. So there are so many examples we can, and I can bring that can be used as composite reinforcement from natural plant materials. So I just have listed advantages and some drawbacks of natural fiber composites. Obviously, there are lots of advantages, high specific strength and stiffness. What I mean that is, if you compare density of glass fiber, it has got 2.5 gram per centimeter cube. If you measure the density of flax fiber, hemp fiber, or jute fiber, they are 1.114. But if you divide by the density to their modulus, the specific modulus will be higher for glass fiber than higher for flax fiber than glass fiber composite. So there are so many advantages we can tap from these natural materials. So low processing energy, renewable sources, low emission, and so on. And then obviously there are challenges. These materials, they absorb moisture, they have got low durability, they have lower performance. There are no standard available yet because still there are new materials. They have lower flame retardance behavior. If you want to use flax fiber, hemp fiber, jute fiber in furniture, for example, or in aerospace applications, the basic requirement you have to meet is flammability aspect, fire retardance behavior. If you cannot meet that, no point talking about it. But then there are other applications where you don't need that property. So we need to find the application niche area. Where are the areas that we can use this material? So that we can bring sustainable materials. Well, I have talked a lot about the composite materials and their applications. So aerospace, marine, wind turbine, automotive, construction, furniture, we can give so many examples. So one of the things that we have been doing in our research group is, one of the research areas is light weighting. How can you reduce the weight of the material? Whether it is for any application, if you can reduce the weight, you can reduce, just to give an example. In automotive application, for example, if you have got lower weight, you have got less weight to carry. If you have less weight to carry, you have got less fuel consumption. If you have less fuel consumption, you have less CO2 emission. If you have less CO2 emission, you have less global warming potential. So there is always a link. So road transport contributes significant amount of greenhouse gases. As I mentioned earlier, OEMs, original equipment manufacturers such as Ford, Mercedes, Audi, Jaguar Land Rover, just give name, they all are moving towards lightweighting so that they can reduce the overall weight and they can reduce the greenhouse gases from coming from the automotive sector. Right, so in terms of their lightweight, their life cycle performance, these composites are far better than conventional composite. So just an example, you reduce the regulation that you want to reduce CO2 emission from 132.2 kilometer to 90.95 gram by 2020. This is already happening. So USA is already happening from 28 miles per gallon to 54 point. So can you see how much they want to increase? So how can you achieve that? Obviously, these are achieved by lightweighting. One of the areas you can do is lightweighting. This obviously there are other areas as well. So I've just given one example. If you have got 16-inch wheel that produced by SABIC, if you use carbon fiber reinforced plastic, you have got 3 kilogram weight. If you use aluminium, you have got 5.8. If you use iron, ferrous, then you have got 15.8 per kilogram. So you can see how much weight you can reduce just by changing materials. So if you automotive industry, they want to reduce the CO2 emission, so they can go to new technology. Obviously, electric vehicle is there now. There are high performance, parts. Engine transmission is another area. Packaging and fuel tank volume is also another area that can contribute to reduce CO2. And another area is lightweight material. So this is what we are working at the moment, is lightweight materials. How can you bring sustainable lightweight materials so that you can reduce the weight, at the same time you can reduce CO2 emission. All right, so this is, so circular economy is important area. If you go to packaging sector, if you go to automotive sector, if you go to renewable energy sector, circular economy is very, very important. So just want to few examples and I want to close. We have been working different materials. So our aim is natural plant fiber-based composite materials have been used in non-structural application for many years. Non-structural application means maybe door lining, parcel shelves, where mechanical performance is not so important. But our aim is how can we not go to next level? How can we not use this material for semi-structural application or even structural application? So for that, we are doing different research work, and this is one of my PhD students' work that I'm presenting. So he used flax fiber vinyl ester composite, and flax fiber vinyl ester composite is stitched, and flax fiber basal fiber hybrid composite. So he was trying to do fracture toughness behavior mode 1. So mode 1 is how, when we apply load, how the crack opens and propagates. So that kind of application is for semi-structural application in certain component. So we work on the flax fiber vinyl ester, flax fiber stitch, because we wanted to stitch that, because if you want to propagate that, you want to arrest the crack. So the material will stay longer. So that was the idea. So stitching was done to arrest the crack. So the crack will propagate less, or it will take longer time to propagate. So we use hybrid technique. So basal fiber was used to hybridize flax fiber, and that gave us some performance improvement. And obviously natural plant fibers composites are vulnerable to environmental exposure, and putting basal fiber gave us another benefit, less vulnerable to moisture absorption. And there was another benefit we achieved from there, I have not presented here, is the flammability aspect, thermal stability. So basal fiber gave thermal stability. Well, so many people talk about basal fibers are same as glass fibers because the processing is almost similar. They consume energy almost same way. That's true in a way, but at least basal comes from rock. Yeah, so that's our argument. So by hybridizing natural plant material reinforcement, you can improve performance. So I was very happy. This PhD scholar, he did mode 1 and mode 2. So his mode 1 paper was published in Composite Structures, and mode 2 paper was published in Composite Science and Technology. So these are very premier journals in our field. If anybody from PhD can produce 2 papers, he has produced many papers, 2 papers in this big journal, job done, almost. It will be a lot easy to go for Viva. Yeah, for PhD Viva. So yeah, so we have a lot of. I'm very privileged and very fortunate to have many scholars, PhD scholars. They do serious work. A lot of collaborative partners doing serious work and producing amazing outputs. So this is another work that we conducted. Here we are looking at impact of this behavior of flax fiber composite, and then we also hybridize carbon fiber to flax fiber. Because carbon fiber, we cannot completely ignore them. That's the challenge. This is amazing material. Obviously, it has got a lot of consequences, but at the same time, these materials are amazing. You cannot fully ignore or fully replace carbon fiber and glass fiber from natural fiber. You have to use them whenever you can take the benefit. Synergistic effect, we call it, hybrid effect. So here we improve impact toughness. Flax alone didn't give amazing toughness behavior, and then we put carbon fiber, then we improve the performance. Similar work we have done looking different materials under different temperature, how this material behave, flax fiber, vinyl ester composite, how they behave under different environmental condition and the temperature. So these are some of the results we have achieved. So again, we have used hemp fiber and we have achieved amazing results. So flax fiber, obviously one of the things that we need to do as an academic research institute is understanding damage behavior of this material. These are new materials. Like steel, we understand how steel fails. We have a long history of steel being used in industrial application. But composite materials, we have got less history, but at least carbon fiber, glass fiber composites, we have got some experience. But with natural fiber composites, we have not much experience as we have experience for those composites. So we need to understand their failure behavior using enhanced techniques. So microcity we use for this understanding damage behavior, and then we use modeling simulation. So we have got other technique we use, lean manufacturing. We're trying to reduce the waste using different lean techniques. So manufacturing using machine learning, digitization of manufacturing. So these are all the areas of work need to be explored using AI in manufacturing. So this is what we are doing in our research group as well. So to stay competitive and to move ahead with these advanced materials, these techniques and process has to be adopted. So this was just one example. We work with University of Bangladesh, just using jute fiber made from very simple technique, hand layout technique, and then we published this paper this very high impact factor journal, Royal Society of Chemical Advances. Okay, so we can work together, we can achieve amazing results, and we can work collaboratively. So I'm very glad today to be here with you. And the program jointly organized in association with Sone UK, and we are very open to work together with NEA. I was a member of NEA. I have I renewed my membership. I think I should renew my membership. I will ask how to renew. So yeah, so these are the areas that we can focus. And the conclusion, the world needs sustainable composite materials, and they can contribute towards circularity and net zero. Advanced materials, including natural fibers, are really good materials for structural, semi-structural application, but still have a long way to go, a lot of challenges. So this is the diagram I really like, and I appreciate that this because this comes from Professor Sriram Ramakrishna, whom I have so much respect. He comes from National University of Singapore, so I got this diagram from him. I love this diagram. You can read, the picture speaks volume. Thank you so much for your attention. I'm very grateful for this opportunity. Yeah. We can use these materials in Nepal. We need to talk to different sector, industry sector. Perhaps building and construction is one sector we can really work together, because the cement, the concrete, they produce amazing amount of greenhouse gases. So if we can work with them and bring them on board and try to bring, we have got hempcrete, we can introduce some natural materials as a reinforcement and try to reduce the conventional steel material, maybe introduce other building materials. Yes, we can do this in Nepal as well. There's no, why not? There's no reason that we cannot use this in Nepal. Obviously, infrastructure-wise, we may have some limitations, but collaboration is the means that we can approach different institutions, different academic institutions, and then we can collaborate.
साथै यो स्लाइड चाहिँ नेपाल इन्जिनियर्सको वेबसाइट उक्ली टक प्रोग्राम भन्ने छ, त्यहाँबाट हजुरले डाउनलोड गरेर हेर्न सक्नुहुनेछ। इन्जिनियर्सको थुप्रै गतिविधिहरूको जानकारी लागि नेपाल इन्जिनियर्सको फेसबुक पेजलाई लाइक गर्नुहोला। आजको यस कार्यक्रमको संयोजन चाहिँ हाम्रो सोसाइटी अफ नेप्लिज इन्जिनियर्स युके सोनिकुले कार्यक्रमबाट संयोजन गर्नुभएको छ। लगातार हामी 4वटा कार्यक्रम सम्पन्न भइसकेको छ सोनिकुको कोर्डिनेसनमा।
नेपाल इन्जिनियर्स एसोसिएसन एभ्री फ्राइडे NEA टक प्रोग्राम लिएर आइरहेको यहाँले थाहै छ र हामी लामो समयदेखि नेपाल इन्जिनियर्स एसोसिएसनले सोनी युके सोसाइटी अफ नेप्लिज इन्जिनियर्स इन युके भन्ने चाहिँ एउटा संस्था छ, त्योसँग लामो समयदेखि हाम्रो चाहिँ एउटा कोलाबोरेसन हुँदै आइरहेको छ र हाम्रो यो कमिटीले पनि यसलाई चाहिँ रिन्यू गऱ्यौँ यो रिलेसनसिपलाई र त्यसपछि हामीले विभिन्न प्रोग्रामहरू चाहिँ भर्चुअल फिजिकल सबै गरिरहेछौँ र नेपालमा आउनुभएका एक्सपर्टहरू जो सोनी युकेसँग आबद्ध हुनुहुन्छ उहाँहरूले हामीलाई जानकारी गराउनुहुन्छ र पक्कै पनि हामी कति पछाडि छौँ आजको प्रेजेन्टेसनबाटै थाहा हुन्छ। आज सोलिड वेस्ट कति ठुलो चुनौती भएको छ, यो हामीले दिनदिनै मिडियाहरूमा सोसियल मिडियामा हेरेर हुन्छौँ। बालेन र सरकार बिचको द्वन्द्व पनि हेरेका थियौँ, सिंहदरबारमा फोहोर नउठाउने कुरा पनि हामीले सुनेका थियौँ। भन्दाखेरि हामी 15 दिनसम्म वेस्टेज नउठ्ने कहीँ उ छ। फेरि जमानामा फोहोरमा मोहर भन्ने चाहिँ न्युज पनि आएको थियो, तर त्यो इम्प्लिमेन्टेसन पार्ट हामी धेरै पछाडि छौँ। यो त्यसले गर्दा चाहिँ अब हामीले मेसेज दिने हो, सायद यो मेसेज गभर्मेन्टका बडीहरूले सुन्नुहुन्छ। यो किसिमको टेक्नोलोजीहरू यति वर्ल्ड वाइड आइसकेको छ, तर हामी नेपाली कति पछाडि छौँ भन्ने कुरा पनि यहाँ देखिएको छ। त्यसले गर्दा फेरि पनि सरलाई विशेष धन्यवाद, सोनी युकेलाई विशेष धन्यवाद र यो हाम्रो रिलेसनसिप सधैँ चलिरहन्छ। हामीले पनि यहाँबाट प्रोग्रामहरू गर्दाखेरि त्यहाँबाट विशेष सपोर्ट भइरहेको हुन्छ। फेरि पनि यहाँ जति पनि उपस्थित हुनुहुन्छ सबैलाई धन्यवाद दिँदै, सोसियल मिडियामा जोड्नु भएको सम्पूर्ण सर म्याडमहरूलाई चाहिँ धन्यवाद दिँदै आगामी दिनहरूमा हामी विभिन्न प्रोग्रामहरू गरिरहेकै हुन्छौँ। अबको 5 गते हामीले एउटा वुमेन कमिटी छ, हामीले एउटा विभिन्न बिजनेस कमिटीहरू बनाएको छ। त्यसले चाहिँ एउटा वुमेन सम्बन्धीको इम्पावरमेन्ट सम्बन्धी र अरू टेक्निकल कार्यक्रम चाहिँ गर्दैछ। त्यसमा चाहिँ सर्टेन हामी मिनिमम केही चार्जेस राखेका छौँ, त्यो गरेर यहाँ पार्टिसिपेट हुन सक्नुहुन्छ एउटा मैले सूचना पनि दिएँ। र यसै लगायत एभ्री फ्राइडे केही न केही न्यू टपिकहरूमा हामी आइरहेकै हुन्छौँ, हामीसँग जोडिरहनु होला।